Now let's talk about from the Dirac equation as a brief spinner to the QED as an interaction between the fermions and the gauge boson, U1's gauge interactions. And the first of all, such Dirac equations that comes from the relativity quantum mechanics, the Schrödinger equations with the insertions of the energy and the momentums of particles as the derivatives of the space-time and the relation between energy and three momentums and the mass in the relativistic theory. So the result is the Klein-Gordon equations, which is the form as the Helmholtz equation. And the first the partials mean the propagations and the amplitudes mean the pies. And so we can construct the such a propagation equation for the spinor, which is the equation. And for the Lorentz invariance, there are gamma matrices are inserted for the such Lorentz transformations of the spinor. So the Lagrangians are written by that. So for the Lorentz invariant scalar with as joint spinor and the gamma matrix. So psi bar and the gamma and the psi is a Lorentz invariant scalar. And if we multiply such a factors, then the equations are reduced in the Klein-Gordon equation as the propagation equation. And the gamma matrix is the construct with the power matrix as a 4x4 matrix, where the sigma mu and the sigma mu bars are defined like that. And the gamma matrix has a following property: Hermitians and anti-Hermitians and anti-commutative relations between them. And there are two important results in the Dirac equation. The first one is the spin. The Hamiltonian does not commute with the partial angular momentum. There are additional intrinsic spin, which is the construct by the Pauli matrix. So the total angular momentums are conserved. So there are intrinsic spin with the 1/2 for the such a fermion. And the second one is the antimatter. There's negative energy solutions that exist. So the for the minus E, it has a positive energy. So the such antimatter has a backwards time and opposite quantum number. The solution of the Dirac equation is also similar with the plane waves. So if we try such a solution, then the Dirac equations are reduced by that with the two component spinor. And if we choose that the 1 0 and 0 1 as a basis, then the relation between the two components spinor U1 and U2, so the U2s are determined. So there are some of the very typical Dirac equation solutions, like U1 and U2s for the matters, and the V1 and V2s for the antimatters. And each U1 and U2s are actually the each spin eigenside, spin up, spin down, and also for the V1 and V2. And by the charge conjugations applied tested with the gamma matrix, we can swap between the U1 and the V1 matters and antimatter. And there is also one remark, the helicity, which is the relation between the momentum direction and the spin direction. If the momentum and the spin directions are the same, the helicity is the positive, and it is called the right-handed. And if the momentum and the spin directions are different, it is called the left-handed helicity. Such helicity is not Lorentz invariant quantity because in the different prime, the directions of the momentums can be changed, but in the relativistic limit, such helicities cannot be changed by the different prime. So there are some additional other state for this Tx plus of the left-hand and right-hand, which is a chirality. This is the Lorentz invariant quantity as an eigenstates of the gamma bimatrix. So in the relativistic limit, such helicity and the chiralities are signed. So we can assign the helicity eigenstate if the momentum is the directions with some spherical coordinate. Then we can assign the helicity state by the eigenstate. Also, by the parity transformations with the gamma matrix, the right-handed helicity state is the convert to the left-handed and vice versa. So now I want to turn to some of the QED interactions of the such fermion from the pre-fermion. And I will talk about the very tricky derivations of some of the Feynman diagram there are no QPTs in here. There are just our focus on the particle phenomenology. So as the toy model also for the Feynman diagram, the transitions amplitudes can be written by the first order and the second order with the intermediate state chi. So there are two possible diagrams for the scattering from A plus B to the C plus D. There might be some of the intermediate state as a C plus X plus B, where the X is some of the mediators, the bosons here. So if we cut this state, then there are three states C, X, B. But in this diagram, the intermediate state becomes A, X, D. So we can write this the second order term. For this case, is initial energy is EA plus EB, but the intermediate states are EC plus EX plus EB. So and the coupling is given by the G and G because the potentials in here perturbing Hamiltonians are just given by the coupling Z. And the second case, the intermediate state energy is EA, EX, ED, so the denominators are different. So if we add the two possible diagrams, add the amplitude from the two possible diagrams, there are two fractions and the couplings and the remainder Lagrange factors. So if we rearrange and some calculation using the energy conservation, such two fractions that can be written with such a form, and by using the energy momentum relation, the remaining terms, the form one terms case minus mass of the X boson. So it calls propagators for off-shells virtual particle as mediators. And actually the such amplitude is the Fourier transformations of the potential, because the such potentials acting on the initial and the final states, so this becomes the plane waves, and it can be interpreted as the exponential factors during the Fourier transformation. So if the S matrix or amplitudes has some of the propagator form, then the potential is given by the Yukawa potentials, and it reduces it to the Coulomb potential if the mass goes to zero limit. For external field, the spinors contributes as the Feynman diagram and the S matrix as the solutions of the Dirac equation. And also similarly, the externals, the gauge bosons, contributes to the S matrix as a polarization, which is solutions of for the equation of motion for the vector field. For internal field, there will be the appears the propagator term. For the photon propagator, the 2-point correlation functions for the photon field. From the equation of the motion, we can obtain such a Green function, and there are some other polarization state will be the summed as some of the by using the complete relations using the polarization state, we can obtain the photon propagators G minus of the Q square. And the fermions or spinor propagators also similarly by using the Green functions of the equation and the complete relations and the all possible spin state, it becomes the numerators the gamma mu, p mu, so that it can written by the cancel p, so the fermion propagators turning out. So by the QED Lagrangian, we can lead with the Feynman rule. First of all, there are photons kinetic field strength and the Dirac equations as a free fermion on the gauge interaction between the gauge boson and spinor. So from the east, we can lead with the external photon and the external fermion from the Dirac equation, and the propagators for the photon and the propagation for the fermions, and the interactions between the fermions and gauge bosons following. So there are some of the several examples for the 1, 2, 3, 4 scattering as a T channel. We can calculate the S matrix from the Feynman diagram. For the external spinors 1, 2, 3, 4, there are 1, 2, 3, 4, but the outgoing particle there are adjoint spinors P3 and P4. and there are momentum transfers here, and the photon propagator, and the vortex here and here, and all the quantities, these amplitudes, the Lorentz invariant by the contraction between the index mu and nu. This is a U channel exchange of the 3 and 4, so the location of the 3 and 4 exchanges compared with the previous one. And this is a S channel, so the ingoing antimatters V2s are located in here at the joint, and outgoing antimatters P4s are located here as a P4, and the momentum transfers are given by the P1 plus P2 to satisfy the momentum conservation. And this is something like the E gamma, so the E gamma scattering through with the fermions propagators, so that there are fermion propagators are located in here, and they are ingoing photons P2 and the outgoing photons here. And reminds that there are also the all the index are contracts, so the amplitude is the Lorentz invariant scalar here, index of the epsilon mu here, and the vortex, and also vortex and the external photon. This is EE bar gamma gamma, so electron positron annihilation process with the fermion propagators here, and the two photons turns out as a going particle, and also the Lorentz invariant. This is also the E gamma, but as channel case. The all propagators and the ingoings and outgoing fermions and photons, they can be written, and this is as channels to momentum transfers borrowings. Maybe this in the next videos I will discuss the remaining thing, but how can we derive such a complete relations for the spin and the polarization for the fermions and the photons respectively, and how can they obtain this the spin sum as a scarce of the this S matrix and obtain the cross section as angular distributions.